And today we're going to talk about our second in a series of 3 tutorials on unsteady analysis. And in this session, we're going to talk about strategies for working with unsteady CFD results. Many of the things we talk about today, though, could be extended to structural analysis, fluid structure interaction, or even test analysis for this time result. So let me go ahead and we'll get started here. So again, good morning. What we're looking at now is the second session. We actually had a first session where we talked about some of the underlying physics and things that one needs to be aware of when analyzing unsteady results. And today we're going to look at some more practical strategies. We will have a third session which will be a little more of a tutorial in that we'll actually walk through a couple of examples that you will have access to the data and you can follow along. That will be coming up in June. So with that, let's just quickly review where we were. And I'm going to ask her the question. I think this is an important question because some of the things I'm going to show you here today are in a release of Tecplot. So I'm going to ask the question, what version of Tecplot, or are you using Tecplot 360 2011 R1? And if you could go ahead, and I'm going to let this poll go for about 25 seconds. I want to be aware of everyone's time. And I'll wait until I have about 80% who have answered. We're at about 70% right now, 71. Looks like we're going to. Looks like we're at about 80%. I'll go ahead and close that poll. And let me share those results with you. So you can see that we have quite a mixture here. We have nominally, looks like about 40% plus or minus that are using, 20% are using the new version, 40% using an older version, and about 25% not using Tecplot at all. So let's go ahead and continue with the conversation here. So that's important. So some of the things that I'm showing you here today are only available in the newest release of our application, but the strategies are generally applicable. So in session 1, we talked about why people are moving to unsteady analysis. Lots of reasons why that's happening, in particular, just the improvements in computational resources in terms of their speed and overall low cost, as well as some new phenomena. People are much more interested in resolving turbulence, for example, and that was something that was just difficult to do in the past.
That's right. The computer performance was just not there to be able to do that sort of thing. But as we go forward, it'll become more and more common.
So in the second session, what we're going to talk about is a review quickly of the concepts we talked about in the first webinar. Then we'll go into 2 use cases. We'll start with one of these cases we started with in the last session, which is vortex shedding off of the cylinder. In this case, we're going to spend a little more time there and talk about some of the how you might want to quantify those results and ultimately present those results either as animations or in a report. In the second use case, we're going to look at a 2D wind turbine optimization. These data were courtesy of Pointwise. We had a joint webinar that we put on last month where we talked about how you can use a heterogeneous environment using third-party tools to do a 2D wind turbine optimization. And we want to leave plenty of time for Q&A. So as we go along, if you have a question, feel free. So with that, let's quickly just review the concepts we talked about in the first session. And before we do that, we want to get a context of how really how many solution time steps you're looking for or how many you actually are dumping out. So just a quick question. We're looking for how many solution time steps do you dump out for your unsteady simulation? And we'll go ahead and move until we have 80% participation, and we'll close the poll. So again, how many time steps do you output from your simulation? And we're at about 60%. Looks like we're getting close to the 80%. Usually when I get to 80%, we'll try to close that off and show you the results. Okay. Voila, we've hit 80%. Let me go ahead and close that real quick. And I'll share with you what the results are. So you can see that for a significant component of the audience, you're looking at over 1,000 time steps. And that certainly does pose an interesting problem just from reading it off the disk.
Yeah, that's a lot of data. That can take a lot of time, especially if you have fairly high resolution grids.
And certainly that's been one of the things that we're seeing more and more. Is, we're seeing people looking at several thousand time steps, and it's so much data, in fact, they're looking for strategies to reduce that data in some capacity, and we're working with a couple of strategies for that. We won't talk about that here today. Okay, so let's continue on, and we're going to just talk about why there's so much interest in this unsteady analysis, and we talk about moving body simulations, rotorcraft, and biomimetic simulation like this fruit fly that we're showing here on the slide. Of course, acoustics, and that's becoming more and more of an issue, especially in the aerospace industry. I know that there's been a tremendous amount of work Boeing's done with the 787 to reduce noise so that the plane can be validated in a number of different airports.
Yeah, absolutely. Acoustics is often generated by the aerodynamics of the plane, and hence the aeroacoustics. And so these simulations typically use very high resolution CFD methods, and it's and highly resolved in time as well. Okay, so welcome to the fourth dimension. This is time-dependent data. Generally, you're looking at three-dimensional solutions through time. This is actually a review of what we did last time. So the steady-state methods are well established. Unsteady is more difficult, largely because the best we can do on the screen really is looking at three dimensions. So to get to the fourth dimension, you have to use a couple of strategies, one of three or so strategies. One is looking at do something qualitative with animation, so you can actually just watch it, a movie of it changing over time. Or you can do something more quantitative, so you can integrate through time, look at scalars that, or look in the frequency domain through a discrete Fourier transform, or perhaps some sort of statistics. So you look at min, max, and average plus standard deviation over time. Finally, one of the things that we do a lot, and I imagine most people do this, is looking at vector fields. And so there's really there's a change in how the vector field visualization works when you get into time-dependent data. For steady data, Streaklines, Streamlines, and particle paths are all the same thing. But for unsteady data, they're very different.
And we'll spend a little time walking through a couple of examples of how you can use the different strategies, Streaklines and Streamlines, to analyze an unsteady result.
Wow, here we go. This is, I'm not going to go through all the details of this, but let me just summarize by saying that this Streamlines, but all of these things, Streamlines, Streaklines, and particle paths for that matter, are tangent curves, in that what they're tangent to is different. So for a streamline, it's tangent to the vector field at a given time, a constant time. And for the particle path, it's the vector field varying through time. And the same is true with streaklines. But streaklines are actually particles that have been released at the same point periodically, and just connect that with that set of particles to create a line. So for typical things you might want to do in terms of analysis or integration. So mass flow rate, we're going to talk more about this on the next slide. Forces and moments, etc. Another thing you might want to do is actually look at Reynolds average quantities. This is in particular if you're doing turbulent flows. And so that's a different thing. Actually, what you're doing there is you're getting a mean and then some perturbation about the mean. And then finally, looking at the results in the frequency domain is important, especially for things like aeroacoustics. The mass flow, this is an example of a rocket nozzle. and you might want to look at the start of the rocket nozzle, and you might want to look at how the mass flow varies over time, and so that you can see that in the plots in the upper right. Same thing can happen in fuel pumps and in general, actually, in internal flows. You're going to be wanting to look at mass flow.
And the other thing to point out is that because there is so much interest more recently in the heavy lift, the NASA's heavy lift contract, and I know that both ATK, let's see, there was a bunch of people who bid on it, and I think Boeing, SpaceX, Blue Origin, I mean, there's just a whole bunch of people who are working on that, and in that context, certainly what we're seeing is that there's a lot more interest in model design.
Absolutely. Yeah. Obviously, forces and moments are important. This is especially critical if you're looking at the distribution of forces along a structure like a wing or a rotor in this case for a rotorcraft. And so you would want to look at how these things vary over time so you can actually couple this with a structural dynamic code so that you can do aeroelastic analysis.
Well, there seems to be, again, I'm not sure what GoToWebinar seems to have issues with audio, so we're going to switch to a different audio device. And, okay, so hopefully
Welcome
you can hear a little better now.
Welcome to GoToWebinar, like, web events made easy.
Microphone should be a little better, so hopefully that'll address some of the problems with the audio. Okay, let's continue on.
Oh, yes, we mentioned frequency domain analysis. And here we have now in Tecplot a discrete Fourier transform capability, so you can actually look at the results in the frequency domain, so you can get an idea of where your dominant frequencies are and harmonics. That's useful certainly in aeroacoustics, where generally you want to look at your frequency versus some sort of amplitude. But it's also valuable in other areas like aeroelasticity, where if you have a coupling of frequencies from the fluid dynamic frequency and the structural natural frequencies, you can actually end up with flutter and destructive flutter forces. That can also occur, by the way, in airplanes. It's an obvious one, but it can also occur in bridges and buildings, and the classic example of that is the Galloping Gertie down in Tacoma here, where it actually was destroyed in a windstorm from flutter. Yeah.
And I guess we got a couple people who said the audio seems to be much better, so...
Excellent, excellent.
I guess we'll just use the voice over IP for the next one. Okay, so let me get back to asking you questions. So the last question we're going to ask here this morning is around what is the most challenging aspect of your unsteady analysis today? So, in the context of what you're trying to do with your unsteady results, is it the derived quantities? Are you, is it creating animations, or a little bit of each of them? And this will help drive how much time we focus on each one of these functionalities as we go through our use case. So if the primary interest is in animations, for example, then we would spend more time talking about the methodologies for animation creation. And although the results are still coming in, we're at about 70%. And again, when we get to 80, I'll go ahead and close it off. So again, we're looking for what you consider the most challenging aspect of your unsteady analysis today. Okay, so we've hit 80%, a little over actually. Good. So we'll go ahead and close that, and let me just share those results with you. So it looks like, of course, there's about a third or a little over a third of people are saying, well, all of it, which is good. So we'll try to touch on all the disciplines here. One of the things that came up, though, is analysis of common derived quantities, and so we'll spend a little more time talking about how you can quantify results from unsteady simulation. So let's go ahead and close that, and we'll continue on. Okay, so we're going to move into the two use cases, and we're going to start with a very common test case used for validating turbulence models. This is simple flow over a cylinder. Now this is a 3D result, and we'll show you the 3D nature of it here in a moment. We'll talk briefly about loading the data from Plot3D, although we aren't going to actually load the data. We'll start with the layout, and we'll talk about that in a moment. We'll talk about some strategies for quantitative and qualitative analysis, starting with simple exploration of the results over time. We'll talk about streamlines, streaklines, integrations of scalars, and then we'll talk about how you best report on the information. So with that, I'm going to drop into Tecplot 360 2011 R1. Now we do have a release coming out just in a few weeks here, which has some updates to some loaders, in particular Plot3D loader. But these data actually came from Plot3D, and that's something that we have a Plot3D data loader. And for our most recent release, we have been focusing on helping people who are using codes like overflow, where they actually have adaptive mesh.
Right. When you adapt the mesh changes between time steps. Same happens actually potentially for just any unsteady flow where you have unsteady geometric orientations. But in particular, in these cases, you need to be able to read in multiple grid files. And that's something that's new with our last release in this spring or late winter. And before that, you had to go through additional steps to append data, but now you can do it all at once. And we also added some things to speed it up, especially in cases where the grid structure is not changing. So it's if it's a ordered grid, it has the same number of zones and the same dimensions on the zones. It'll read a whole lot faster than it did before.
And one of the things we are seeing for some people now when they're using the adaptive mesh technology and like overflow, they may not have uniform grid structures, and we've actually addressed that in the loader as well.
Right.
So this example comes from Plot3D. You can see it's a pretty simple cylinder in 3D. And if we start with kind of a simple exploration of these data, we'd probably just look at a slice. And in this case, we're looking at vorticity. And if I just look at the vortex shedding over time, we can just look at that very quickly. So I'm just walking through time. There's about 50 time steps here. Another way I might look at that, though, is just change to, say, row, which might be an easier thing to look at. So if we look at row, now you're looking at that vortex, where you can look at the change in row over time. So if I hit play, you can actually see the beginnings of that vortex shedding.
Yeah, this is a classic example of a Kármán vortex street coming off of a cylinder. And this is exactly what drives a lot of the aeroelastic problems, the flutter problems that you have on aircraft as well as on buildings, bridges, cables. This is a big problem I know in the petroleum industry where they have cables holding these these offshore drilling rigs in place, and so this is a significant problem.
And then again, one of the great things about having the additional computational resources is now you can study them in a more dynamic sense. So we're going to go ahead now and take a look at, well, when you talk about presenting the information, there are a couple of things that you want to take advantage of. Specifically, you want to know things like, well, what is the time? And of course, dynamic text is one strategy for that. So if I wanted to have time on screen, I can just add it here by adding in solution time. And that'll bring up solution time. Now, there's I'm actually going to look at not as many significant figures here. So now when we do that same animation, you can see that it's going to update time. So it's a very quick way. If you were going to make an animation for group presentation, you want to make sure you include time. But there's a lot more going on there. And oftentimes, when we think about this, we put in information about time, but we don't put in other information that might be helpful. So if we, for example, take a look at, just bring this up very quickly, we're going to look at a couple of other dynamic text. So one of the things that we looked at was the solution time, but we also have the slice position. So if I change the slice position in my data here, you can see that, in fact, it updates dynamically. Now there's other pieces of information that you bring in when you're looking at analysis that, again, if you talk about automation, that you want to take advantage of. For example, in this context, we're looking at a Mach number of 0.1. Now if you were to look at this, say where you're doing a sweep in Mach, where you may have 10 or 15 different variants, we actually are pulling that directly from the solution. So if we go to the auxiliary data here, you can see that one of the variables that we have is in fact Mach number. So it's the reference Mach, which I'm not seeing here, but there it is, reference Mach number.
Right.
And because that variable is going to be consistent across your simulations, you can actually point to that. So if I go back up here, you can see that, in fact, I'm pointing to that common reference number. So when I go through and use a layout, I'll be able to automate the analysis, automate this, so I can just have it go through and generate a number of animations, and I can put them up on screen and know what the different Mach numbers.
Yeah, it should be pointed out that this data is read from the Plot3D file automatically. So it's in the header for the zones or for the files, and so it's there. And taking advantage of it makes for a much more valuable animation. You can actually get a good feel for what's going on, both qualitatively and through the image, and quantitatively through the auxiliary data.
Now these auxiliary data also can be appended. So if I wanted to add in additional information like the date that this was run, I can add that in and say, put May 12th here. And so that will add in with the data set. So I'll have a new variable, date, which I guess I probably need to add that here. Other things that you could add in with the data set, you might put in who ran the data, or you could put in additional scalars. If you did a calculation of, say, max pressure, you could put that information in as well. And the great thing is these data can be used then in additional calculations.
And that's right. I mean, a lot of times you want to actually compute something from the basic quantities used, for instance, the reference values. If you have reference pressure in your auxiliary data, you might want to utilize that in a calculation of reference, well, say it's reference velocity. You might want to use it in the calculation of a Reynolds number. And if you don't have Reynolds number in your auxiliary data, you can actually calculate it and use it in and put that in the plot.
Now the other thing that you could do, if I wanted to add in date, so I can put in date here now, and then I can use this aux data and put that dynamically on. So just to illustrate that very quickly, you can see that if I put this in here now, I can just put date. I think that's what we called it. So.
Mm-hmm.
Oops. Do that in parentheses.
Another place you can use the auxiliary data is in the data alter, and you can use a common way of using it there is, for example, computing coefficients, pressure coefficient from the reference pressure and reference, velocity.
So although it's convenient to look at a slice, when you're thinking about vortex shedding, often people will want to use an isosurface where they could show what's going on in space. So this is really a 3D contour level. So here's an example now where we're looking at the same data. Again, we have auxiliary data where we're showing where that isosurface is. This is a vorticity magnitude of 1,000. If we decided to change that to, say, 150, this is tied in. And again, this is a good strategy if you're actually looking at multiple solutions, as you'll know right away which variables and at what level you're looking at, which can be helpful if you need to reproduce this. Same kind of thing we can do in animation here. So if I animate now, you can see that vortex shedding. It's worth pointing out that this is a derived quantity. That is the vortex, or the isosurface is both the vorticity is derived, which means it's being calculated on the fly, as are the calculation for the isosurface.
Yeah, exactly. That allows you to get started faster, and it'll be use less memory overall.
Mm-hmm. So if this was in fact what we were interested in, and we wanted to present this information, so you can see that as we go through here, I'll go ahead and pause. I'll go back to the beginning of the simulation. One thing I might want to do is look at the principal axes views, and we can do that pretty quickly now in Tecplot. If you need to look at
principal axes views, we can just select kind of an XY, in this case the YZ, the Y or XY and the XZ, in this case the projections. We'll spit those data in very quickly, and you can get a sense these are all now synced in time. And so this is my original view, and if I wanted to animate now, as I hit animate, it's actually going to animate all of these independently because they are not independently, simultaneously because they're linked together. It is computationally intensive, and depending on your computational resources, the first time you go through this, it could be a little slow, but not overly.
I think it's, fluid dynamically, it's worth noting that this is not a simple two-dimensional calculation. You can see the three-dimensionality in the vortices. I believe this is actually at a slight angle, and that leads to these instability of your vortices and the secondary vortices forming.
And if we wanted to actually look at those vortices, maybe the best way to do that would be to look at a series of streamlines. So on Streamlines and Streaklines, and we're going to look at a little of both. Let's start off with a simple stream trace here. Now again, as Scott pointed out, this stream trace is at any given time step. So if I animate through, you can see that it's changing with each time step.
Right, it's recalculating the whole stream trace on each time step. So that's valuable to tell you what the direction of the velocity vectors are. But it's not really telling you what a particle would do. A real particle will change. You'd have to use particle paths for that or streamlines.
Now, in a way, though, you can see the areas of recirculation and the vortex shedding just by looking at the streamlines. Oh, yeah. But again, that's, as Scott pointed out, at any given time step. But what we want to understand is how are things changing as a function of time, and we're going to use Streaklines for that. So we're going to go in and calculate those streamlines or Streaklines here. So we're going to quickly get rid of the slice so that we can see this. We'll turn off the stream traces so it'll just be a little easier to use. And we'll go ahead and release 5 particles per time step. Now we can actually have our integration time step work with the solution time levels, or we could actually go with the unit solution time. And you can also adjust the delta t that is within the release.
Right. The integration time actually is that you would adjust that if it looks like it's actually jumping too far and giving you odd results. But generally, you want to tie your release like this to the solution time because that's more meaningful.
So just to put it in context, if we watch now how those are developing in time, you can see it's very different than what we were seeing when we were looking at these streamlines.
Now remember what we're doing here is we're releasing these at each of the seed points for the streamlines that we had earlier. So at each of those seed points, it's releasing 5 particles per time step, and it doesn't release them all at once. It releases them at a period throughout the time step.
And just to illustrate that, you can see the difference between the Streaklines and Streamlines just by animating them at the same time. Okay, so you can see that they're obviously different in this case. So when it comes to presenting this information, let's assume for the sake of argument you were more interested in the Streamlines versus the Streaklines. I'll go ahead and stop this. You may actually want to look at multiple views of that shedding to get an understanding of what's going on. So I'm just going to change this from one frame to a series of frames. So now what we're looking at is kind of edge on. These aren't exactly principal views, they are skewed, but we're looking at 4 views of that same cylinder where we're looking now at the streamlines, and I'll go ahead and animate this as well. And it can be helpful because now you can actually see edge on how the area of the circulation is moving as a function of time.
Yeah, again, this is 3-dimensional and we're projecting it to a 2-dimensional screen, so the more views you can get at it, the better, more holistic your understanding of the flow field will be.
Absolutely. So again, there are a couple of questions, but we'll try to. Okay, well, boy, Amolio, a couple other questions. So we have a fair amount of questions here, but we're going to try to address most of those as we get to a good stop point here. So that's kind of, I think we talked a little bit about the qualitative information. We talked a little bit about how you can use auxiliary data for additional calculation, but we're going to spend, in our second use case, we'll spend most of our time talking about some of the integrated results. So can you please comment on the simultaneous animation of flow fields with discrete particles? I don't know if we want to try to add that in here. The discrete particles, I assume you're talking about the streakline analysis.
Right. The streakline is discrete particles released repeatedly at the same point, and I think, I don't know if we showed that or not. That does work. You can do that.
Yeah, and we were going to show masked particles, but I guess we won't do that in this example, but perhaps in the next.
Okay. Sure. Yeah, that works. Not sure what else to say about that.
Okay. Great. Let's see here. Then let's talk quickly about our second use case. Before we do that, I just wanted to thank the folks at Pointwise who allowed us to use this data. If you're interested, we have the recording for the parametric optimization for vertical axis wind turbine designs using independent CFD tools. That is available online, so if you're interested, you can actually go back and watch that webinar. With that, let's talk about our second use case. So in this case, we're going to look at the data used in that webinar. We're going to look at an optimization of an airflow for a vertical wind turbine, and we're going to look at loading the results. These results came from Fluent. We'll talk about streamline analysis. In particular, we'll spend a lot of time talking about integration of scalars, comparing results, and then how one creates animations and/or static images to use in reports, and we'll talk about that in detail. So let's go back to Tecplot here, and let's actually bring up that result. We'll start with just a simple view of the data. Now these data came from Fluent, and we can learn about that again if you go to the dataset info, and if you take a look at where your data come from, you can find out, for example, for all the data, you can get what the data set, where they came from. And you can also learn, where the data were loaded, what the data file was. The data set, in this case, was Fluent 6.3.26. And
I was just going to say, this is a vertical wind turbine. So we're looking down from the top on this, and so it's got 3 blades, and the flow would be from the side, and so you're seeing how it would rotate now.
Mm-hmm. And so what we're looking at here is I'm just actually walking through the time. You can see it goes through about 5 or 6 rotations. Again, the one cool thing about the way that we handle data, the first time we load the data, we actually don't load it till it's needed. Now this is really important if you're looking at 1,000 time steps, which some of you are. If you have 1,000 time steps, and let's say that your average 1 time steps on 10 million cells, which is probably not atypical. Okay, you're looking at not quite a terabyte, but probably 50 gigabytes of data, maybe more.
Yeah. So a terabyte takes a couple of hours just to read. I mean, that's just the physical time it takes to read it off a disk. So a typical hard disk you would have on a workstation. So to read it off of that would be it's in the tens of minutes. It's a significant amount of time. So doing what we do, where you're actually just loading the data you need to show the image, can substantially speed up the initial image, certainly, and then also a lot of times you don't go through an entire animation from beginning to end. You go a certain distance,
right.
And so if you had loaded it all, that would have just been wasted effort and wasted time. So in that scenario,
and we're working on strategies to make that even faster. And towards the middle of this year, maybe in Q3, we should have an application that will be much, much faster for the use case where you have multiple solution files. So that's something that we're working on today. But what we wanted to talk about in particular is looking at, say, the integrated pressure. So if we wanted to look at any one of these blades, and in this case, we're looking at, and I'll bring the zone styles dialog over. This is the, first domain. If we click here, okay, that's blade 7. So let's say that we wanted to look at the pressure as a function of time for blade 7. So we'll select a scalar integral of pressure, and we'll use the time strand. And actually, let's just select blade 7. There we go. Then we'll go ahead and integrate, and we're going to plot those results in a separate window. So what Tecplot's doing, you can see under the scenes, it's actually so fast you can't see it. So here are the integrated pressures for each solution time. So you can see that we have about 100. And it also gives you the max, the mean, and the standard deviation for the total pressure on the blade. And let's close some of the things so you can see it. So I'll close this momentarily. So if we look at pressure, let's go ahead and turn on the contour of pressure. And this is you can see we're just using the line contour representation. It doesn't really matter for this. And we're going to go ahead and go back and we'll do that same animation. So now you can see that pressure variation, and you can also see simultaneously what that total pressure looks like on that blade as a function of solution time. And you can see we have a marker here that shows us where we are. So if I saw something of interest and I say stop the simulation here, I can then go through and probe what those values are. So in this case, we're looking at a value of minus 133. Now I can also probe in the main data set here. You can see that my pressure is about minus 96 at that level. If I move in time, you can see that at that point it's going to continue to give me data. So no matter where I am in this simulation in time, my probe is always going to be active at that point. Okay, we're gonna.
Yeah, this is a the vertical line, the marker, is a new thing that's I believe very valuable in giving people an understanding of how the two plots relate. You can also see this is interesting. There's a lot of high frequency oscillations in this plot, as well as the lower frequency that represents the variation throughout the rotation of the blade.
And then to better understand that frequency, we'll go ahead then and apply a Fourier transform where we'll look at solution time versus total pressure. And we'll go ahead and select the data, and we'll go ahead and do a transform. And what you can see now is we're actually, you can see those frequency. Now, one thing to point out is that you can see that it's always embedded here, and in a way that can be difficult to see. So if I want to expand these frames, I can just apply and move them into kind of a tiled representation where we have now the actual CFD data here. This is the total pressure, and then the frequency is down below. So with the frequency, you can dive in a little bit, and we can try to understand if we probe what those frequency are. So they're at about, which is nice to know, relatively high frequency, and there's the other frequency. So
yeah, so the lower frequency would represent the actual rotation of the blade, and higher frequency is probably some input turbulence, input into the code.
And if we go back now and just quickly animate this, again you have that nice time marker which shows where I am in time. Mm-hmm. Okay, so we talked about how one can do integrations. And let's see, there's a bunch of questions about the FFT. The FFT is new to Tecplot 360 2011 R1. So
what was that? April release?
Mm-hmm. Yeah, April release. So it's relatively new. If you don't have access to it, I'd encourage you to, if you're on license maintenance, you can go ahead and download it from our website. And if you are interested in taking a look at it, you can certainly download an evaluation copy as well.
Now, we've been saying fast Fourier transform, but it actually can handle non-uniform time steps. So in fact, it really is a discrete Fourier transform.
So now I'm going to shift gears a little bit and talk about how does one look at, say, the vorticity. So we talked about some integrated quantities, but if we look at the qualitative information as well, what we're going to look at is that same model, and now you're looking at the vortex shedding. And one of the key things to point out that this is the optimized design, and I'll show here in a moment what makes this design better than the original, I think it was a NACA 5 airfoil. So this, as you can see, it actually has kind of uniform shedding of the vortices here.
Yeah. major shedding being down at the bottom.
Mm-hmm. And that's nice to get that even pressure. Now the vertical there's two kinds of, there's a Darius type wind turbine, which in this case is you're looking to maximize the lift effectively. Pause this real quick. So one of the things that I talk about often is the fact that this is being done, we're computing this. If I hit play now, you'll see that once the data has been computed and it's in memory, it's going to be really fast.
Yeah.
And that's just, again, the way that we handle memory. So you can see once it catches up in time, it will go ahead and slow down a little bit. So this is for one case. What if we want to compare two of them? Let's go ahead and look at that very quickly. So now what I'm going to do is bring in the original case, and we're going to look at that in the context of, so here's the optimized case, or this is the optimized case, and this is the original airfoil. And we'll go ahead and do the same thing, and you can see now that there's some marked differences. In particular, we have this vortice forming at the tip of the airfoil.
Yeah, that's a leading edge separation bubble that's forming on the airfoil, and that reduces the efficiency of the wind turbine because it's expending energy and generating this auxiliary vortex. So if you can get rid of that, you're going to have a more efficient wind tunnel. And my understanding is the folks at Pointwise and one of their customers actually went through an optimization technique to actually alter the wind turbine or the airfoil shape so that it eliminated that leading edge boundary layer separation.
And you can see that pretty clearly in the comparison between the two results.
Right.
Okay. So that's at least from a qualitative standpoint. Again, once the data has been calculated, you see it goes much faster. But if we wanted to compare, say, multiple solutions and actually understand from a quantitative perspective what those net changes are in drag on the airfoil, we can look at all the data. So in this case, I'm going to bring in 4 intermediate steps as well as some integrated quantities so we can take a look at those simultaneously. And we're looking at, I think it's about maybe 5 to 6 gigabytes of data that I have to load off the disk. And that really is the slowest piece for Tecplot at this point, is loading those data off the disk.
Yeah, and so what we're looking at here is the stages in the optimization. So
we have our initial,
up in the, I think the upper right station.
Yeah, the initial design, and then we're kind of walking towards the final design. And so if we go back again, all of these are linked together, and it's very easy to see. So there's that leading edge separation. And if I hit play, Tecplot's going to go through now, and it's going to be, again, calculating. It's a fair amount of data, so it's computationally intensive, and I may not let it go through organically. I may just move the time slider to a couple of points of interest. And what I've done is taken a look then at the delta from the integrated pressures from the different designs. And what we're looking at is just that optimization here, where you can see that you get about, if you were to look at the delta here, it's about a 20% improvement, which is what this really is representing here, the way that the data is presented. So it's about a 20% improvement in the drag, which is pretty significant.
Yeah. And the nice thing about this array of plots is that you can really see it all at once. And yeah, it takes a little while to animate this. Jarrell's working on his laptop, so it's not the fastest machine around. But you can animate it once, and the second time through it's much faster and give you a real holistic view of the optimization process you went through.
And in general, it's to be pointed out, this machine is not overly slow. It's a quad-core machine with 8 gigs of RAM, and I have a pretty fast video card, so it may be a laptop, but it's a nice laptop. Okay.
I wasn't trying to diss your laptop, Darrell.
Okay. We'd never do that. So.
I'd never do that.
All right. Well, we're going to have plenty of time for questions, so that's really what we wanted to show in terms of this use case. A couple things to point out. If I wanted to dump out these animations, that typically what I would do is do this to a file, and there's so many different file formats out there, and certainly AVI is probably one of the more common, but we have of course, added in MPEG-4 and Windows Media video, which seems to have the best compatibility with PowerPoint, but that's not always true. PowerPoint's a unique application, and it seems to have it's a very finicky app when it comes to how it handles video files. So.
Yeah, and one of our new formats, I believe this was last spring, is the MPEG-4, and so that's valuable, especially if you're going to put it out on the web. I believe that's a more standard format than some of the others.
And if we were to dump this out, one thing to point out, and I'm not actually going to let it go through the complete thing here, but if I generate the animation file, one cool thing about the way that we do this is we do it behind the scenes, which it's not going to be rendering on screen, which is nice because it's wasted computational resources to be trying to refresh the image. So we can do this for, say, all the frames in this work area, and if I show this, it will actually just be, I can dump it out there, I guess it's fine. So nothing changes on screen, which is great. So you don't have to wait for rendering. It's rendering off screen, which is great, which means you can do this in batch mode. Everything I've shown here basically can be done in an automated way. Okay. So we'll let that do what it's doing while we go back in. Okay. So we talked about the data came from Fluent. We did some Streamline. We didn't actually look at Streamlines in great detail. We talked about comparing results and creating animations. At this point, we wanted to keep this last couple of minutes available for answering questions. So let me quickly summarize, and then we'll get to a Q&A. So we talked about the fact that when CFD is really, as a discipline, maturing and people are moving to unsteady analysis, we're adding, as you get to the fourth dimension, you really do have to look at different ways of analyzing your data, not just the qualitative animations, but both the integrated quantities and discrete Fourier transforms, or FFTs, as well. And we see this as something that will be continuing to grow. In fact, recently we were out with one of our customers locally here in Bellevue, Washington, just up the street in Everett. We asked the question, are you moving to unsteady? And it was a resounding yes, we're all moving that direction. So yeah. It's good to see.
Yeah, as the computer power continues to improve, we will see both larger cases and more unsteady cases. It's just has to happen.
Has to happen. Okay, so we kind of went through what we had planned to cover for some of the strategies for looking at unsteady simulation reporting. Next, we will have a third session where we get into great detail and actually go through an example where the data will be available for you to go through as well. And at this point, we'd like to open it up to questions. We have a fair number of questions that came in via the question dialogue. And I'll actually see if I can bring lots. I don't know if you can bring them over that easily, so I'll just bring them over here. And if you'd like to raise your hand, go ahead and do so. You'll see there's a little button, looks like a hand. If you raise your hand, then we can go ahead and call on you, and you can go ahead and ask a question. So if you're interested and you have a question, go ahead and raise your hand. And Molio, you have a question, so we'll start with Molio. I'm going to go ahead and unmute you. Okay, Molio, you're on. Sorry, Molio, we're having
some problems here.
Difficult time hearing you. So let me try that again. Sorry, one more time, Molio. I don't know.
We're still having a hard time hearing you.
Yeah, I'm not sure.
Maybe it's coming through here.
No, it shouldn't be. Shouldn't be. Okay. Well, sorry about that, Molio. I guess we'll have to stick to the written questions as we GoToWebinar continues to have issues with their audio. God only knows why. So let's see if we can go through. We've got some questions about data loaders. We'll take those offline. Before you talk about unsteady 4D data, could you talk about unsteady XY plots? That's a good question. I think you're probably talking about in the context of either animating through plots themselves. So maybe if I hop over here real quick. There's, oh, this is still, I'm not going to let this animate off screen, so it's too much time for that. There's two ways to think of that. There's what we call animation, like in this case where we're looking at a time-dependent XY plot. But for those people who are somewhat familiar with Tecplot, there is another way that you can animate this. And if I go in here, you can see that I have a number of maps. And if I go to animate, I can actually animate those mappings. So that's another way to do that in time. I guess if you think of each line as time dependent.
Right, right. Yeah, that would be the mechanism at this point.
There was a question about data size. In particular, can you load data files, grids of 2 million cells? That's pretty small, actually.
Yeah, 2 million is not a problem. We recently have been loading data files of 600 million cells, tetrahedral cells, up to a billion tetrahedral cells. Now it requires a substantial amount of memory to do that. In my case, it was 48 gigabytes. Windows machine, 64-bit Windows with 48 gigabytes, I can load a billion cell case. Mm-hmm. So that'll give you an idea of requirements. 2 million is quite easy.
Yeah, and on my underpowered laptop, I can load about about 50 to 100 million without too much problem. So, let's see. There's a question about can we handle chimera grids with hole cutting?
Yes. We can. Yeah, that would be using the blanking feature. So, for instance, if you're loading an overflow data set, I believe. Wasn't one of these overflow?
Yeah, one of them was overflow, and
yeah,
and that's under we have some blanking capability, which under value blanking it probably should be in a different set here. But the value blanking that we have, you can have up to 8 scalars, so you can include like eye blanking and other ways to blank the data.
Yeah, so overflow, for instance, traditionally has an eye blank variable that is 0 or 1, and you just blank based on that variable, and it'll cut out regions of the grid, and they won't be visible.
Okay. Let's see. There was a question about whether or not you can plot force vectors, integrated quantities on a moving body in the animation. Not sure how best to do that. I mean, that's kind of an interesting one.
Yeah, that's a good idea actually. I don't off the top of my head know an easy way to do that. I'm sure I know you could make it happen by creating a separate series of zones that have one vector in each, and then animate through those. But yeah, I don't know an easy way to do that at this point.
Okay, let's see. Boy, we've still got a bunch of questions here. We'll try to get to as many as possible. We only have about 5 minutes, so let me see if I can get through this quickly. Can you simply drag and drop the date instead of pointing to it? At this point you can't, but that's another pretty good suggestion.
Yeah, that's a good idea.
GIF animation would be good. Again, that's a format we haven't considered in the past, but may not actually do that in the short term anyway. Tom Chan, who is our product planner for 360, I believe he listened in, so he can certainly put that on his backlog. Can you make time average of a variable over solution time and produce a contour plot? That's also another. I don't know how you do that one.
So okay, so I believe you're saying that you would have, say you have 100 solution times. You want to average over those times and just look at that average. That's a good question. I would have to think about that. I'm sure there's a way to do it using, for instance, data alter and a macro that's not particularly a satisfying answer, but I'm not sure of an easier way to do that at this point.
Okay, we have time for just a couple more questions. Okay, can you average over several slices? So yes, that's actually a pretty easy one to do. Let's go back to use case 1 here for a moment. So here's, if in fact I wanted to average over multiple slices, right now I'm only showing a slice, but in principle if you had, well, let's see, at least an n slice here, so at least have 2. One can integrate those provided that they're extracted. So if I wanted to extract these slices so that I can do some computation on them over time, I can do that, and that'll actually just bring those together, and then I can integrate them. So that, good question, but yeah, it can be done pretty easily. I have a macro that does a time averaging per node. That might be interesting, actually, if you want to send that along. So, let's see. Have you seen anyone using vortex method from UCB for the generation of unsteady fluid data?
No, I'm not familiar with that.
Okay, let's see. We have enough time for perhaps 2 questions. There was a question on Kiva 3.4 output, and I believe we do handle Kiva data. I'm not sure.
We have a Kiva loader. I don't off the top of my head know if we can handle 3.4 or not. Yeah.
Okay. What about CFX? Typically, the folks who are using CFX today have been using CGNS as an intermediate format. We've actually talked through to a number of people, generating that additional data may be something to consider because the CGNS format is so portable to other simulations, but we do not have a direct CFX data loader. They do output Tecplot as well, but I'd recommend CGNS.
Yeah, so that's right.
Question, we have time for one more question. There's still a whole bunch of questions here that we'll take offline. Is there any efficient way to load hundreds of solutions from an in-house code and create animation with Tecplot? Or do you have to do it one by one? And well, the short answer is if it's in Tecplot format, you can actually load them all simultaneously and make an animation.
That's the best way, is to go ahead and, especially if it's your own code you're developing or one of your colleagues is developing, you can use the TechIO library to actually directly generate a Tecplot file, and Tecplot is optimized to read Tecplot files rapidly, and so that's the fastest way. Yeah.
Okay. We have time for one additional question. So let's see. There's some question. Is it possible to extract a subset a grid and perform integration on that? And again, it's kind of the same thing I'm talking about here, in that if I did that integration of a scalar value like, I don't know, just a row, and we do that over a time strand, I can select the slice that I just did, the 2 slices here, and we can go ahead and integrate that. So the short answer is, if you have a subzone, you can integrate, and one of the things you can do is exclude blanked regions. So if you do some blanking to get that subzone, then you just say, hey, don't use the data that's being blanked. So that can answer that. Okay. Well, we're coming to the end of our time, so I wanted to take this moment to thank everyone who sat in today. Again, we have a 3rd session coming up, which will be more of a tutorial. In advance of that tutorial, we will make data available to you that you can follow along with, provided you have access to Tecplot. Thanks again for joining us. We really appreciate it. And if you have any comments and you want to ask additional questions, you can send those directly to support@tecplot.com. Thank you again for joining us.
Thank you, folks.
And we'll see you next month.